Hi, this is Dokyung, a PhD student at UC Irvine. Today, I'm going to be presenting our paper, Agamotto, Accelerating Kernel Driver Fuzzing with Lightweight Virtual Machine Checkpoints. This is a joint work with my collaborators from UC Irvine, TU Berlin, and KAIST. Device drivers are still vulnerable today in 2020. A number of vulnerabilities were found and published just a couple of months ago in a GPU display driver, a widely used device driver out there. Now, why do vulnerabilities in device drivers matter? First of all, device drivers are highly privileged as they run within the kernel context alongside other kernel components, and there's no privilege separation between them. The second reason is that device drivers expose a wider attack surface than other kernel components. In addition to the system call attack surface, device drivers also expose a peripheral attack surface, which is reachable by an attacker through interfaces like PCI or USB. Now, let's take a quick look at how device drivers typically work internally. Device driver implementations are state-oriented, where each state transitions to one another based on a narrow set of inputs. In this example state diagram shown on the slide, the device driver first gets discovered, initialized, and then started, and then starts to receive events that are queued into the event queue, which is then dequeued by a separate kernel thread, and it starts to process the payload of the event. What is the problem when it comes to fuzzing device drivers? Fuzzing, by the way, in a nutshell, is a popular vulnerability discovery technique that runs a program on an automatically generated sequence of test cases until it finds a vulnerability as it manifests as a program crash. The problem is that fuzzing device drivers is slow. Executing a test case like the one shown on the slide that lets the driver transition through several states is very time-consuming, which easily takes several seconds. One of the reasons is that device drivers are given CPU time with low priority, and they're frequently interrupted by more important tasks in the kernel. The problem gets exacerbated by crashes, especially repeated crashes caused by so-called shallow bugs. When the fuzzer hits a bug, it can corrupt the system state, which typically requires a reboot for recovering from a possible corruption. Such crash recovery can take tens of seconds, and fuzzing becomes even slower, making it hard to reach deep bugs with the presence of shallow bugs. Because as I just mentioned, the fuzzer just repeatedly hits that shallow bug. An existing approach to address this problem is to use snapshot techniques. Snapshot techniques allow clean state fuzzing where no residual state transfers between test case executions, even after a test case causes a system crash. Existing tools typically create a single snapshot at program startup, and a system crash can be recovered relatively quickly by restoring to that snapshot after each test case execution. However, despite this advantage, some fuzzers do not use snapshot techniques, in part because snapshot techniques themselves add a runtime overhead. Snapshot techniques that capture kernel components can be even more costly. VM emulation or unoptimized full VM snapshot techniques used by existing tools is unfortunately slow. With these existing approaches in mind, we designed the following dynamic checkpointing approach, which is a form of snapshot-based approach. But in contrast to existing approaches, we dynamically create multiple snapshots or checkpoints while actively executing the test cases. Using the example shown on the slide, let me illustrate how dynamic checkpointing helps accelerate kernel driver fuzzing. After the system has been initialized, we create the first checkpoint, which we call the root checkpoint, just like other snapshot-based fuzzers would create. But what we also do here is to create secondary checkpoints while executing test cases. We create checkpoint A here after initialization of the device driver, and checkpoint B here after starting the device driver. We create checkpoints according to a policy I'll get to shortly. So what this allows us to do is, let's say the fuzzer now generates a test case that shares the same prefix as the previous one. We can skip executing the same prefix by restoring the system from the checkpoint B. Moreover, because this is a snapshot-based approach, when we encounter a bug or a system crash, we can restore the system from any of the available checkpoints created during a fuzzing run, not just from the root checkpoint, but also from other checkpoints, depending on the prefix of the next input. Effectively creating checkpoints dynamically while executing test cases allows us to fuzz deep code paths much more efficiently and with no interference between the test cases. As we fast forward not only through repeated crashes, but also through repeatedly executed parts of test cases. As I mentioned earlier, checkpointing and checkpoint restoration themselves add a runtime overhead. To reduce their impact on the overall fuzzing speed, we perform incremental checkpointing. Checkpoints are incrementally created and stored in a checkpoint tree. The root checkpoint node in the checkpoint tree contains the full system snapshot, and other nodes simply store the pages modified, dirtied from the point in time where their parent nodes were created. We also use an optimized checkpoint restoration algorithm. Let me use this example shown on the slide where we restore the VM from a dirty state labeled as D to a checkpoint node labeled as C. Before describing our optimization, let me first consider a naive approach for comparison purposes. In this naive approach, starting from the root node, all the incremental checkpoints are on the path from the root to the node C will be restored. So the overhead of this is proportional to the number of all pages plus 30 pages, because the root checkpoint is a full system snapshot, which already contains all memory pages. In contrast, we take a bottom-up approach to reduce the overhead. In our approach, we first compute the dirty pages of both the node D and node C with respect to their common ancestor node. The combined set of dirty pages represents the set of memory pages that need restoring. We only restore this set of pages that absolutely need restoring. And by traversing the checkpoint tree in a bottom-up fashion, we only restore each of the page only once. This way, the overhead is now proportional to only the number of dirty pages, not all pages. Because most test cases generated by the fuzzer do not significantly modify or dirty the system state, this approach leads to up to 8.9 times faster checkpoint restoration in practice. Although we reduce the runtime and memory overhead of checkpoints, we need to decide when to create them and what checkpoint to remove when we run out of memory. To that end, we design checkpoint management policies. The goal here is to increase the utility of checkpoints while minimizing the impact of checkpointing on the fuzzing speed. The high-level idea here is that we prevent excessive checkpoint creation with checkpoint creation policies and evict checkpoints with checkpoint eviction policies. Let me describe the checkpoint creation policies now. For details on checkpoint eviction policies, please take a look at the paper. So there's a test case denoted by T, which contains a sequence of 5 actions: connect, initialize, start, followed by 2 queue operations. And T prime here is a test case mutated from T on the first queue operation or the 4th action. While executing T prime, there is 5 candidate points in which checkpoints can be created. A naive approach would create a checkpoint after each action. However, we found this approach to be too expensive due to both the checkpoint creation overhead and the memory pressure it adds to the checkpoint storage. So we create checkpoints based on the following 2 criteria. First, we checkpoint at increasing intervals because it is more likely for the fuzzer to generate test cases that match shorter prefixes. And we disable checkpointing at first mutation in executing each test case because most of the mutations in a fuzzing run do not cause new coverage to be discovered. We implemented the presented ideas in a system called Agamotto based on a recent version of QEMU and Linux KVM. For evaluation, we used Syzkaller for USB fuzzing and used our own PCI fuzzer for PCI fuzzing. We ran 32 parallel fuzzing instances and used 12 gigabytes of checkpoint pool per instance. We tested 8 USB drivers and 4 PCI drivers in Linux. An important thing to note here is that we didn't modify the fuzzing algorithms of the fuzzers we used, which was our conservative evaluation effort, or an effort to prevent us from potentially overfitting our checkpointing policies to the sequence of test cases generated by a specific fuzzing algorithm. Due to limited time, I'll highlight some of the key results presented in the paper. These graphs show Syzkaller-USB fuzzing throughput. Throughput here is defined to be the number of test cases executed per second. There are 3 different configurations here. The first configuration denotes a full-fledged Agamotto, and the second denotes Agamotto with only the root checkpoint enabled and without secondary checkpoints, representing a single snapshot system. The third configuration denotes an unmodified Syzkaller, which does not use a snapshot approach. For each configuration for each driver, we ran the experiment 3 times. Let's start by comparing snapshot approaches to non-snapshot approach. The advantage of snapshot is clearly visible when we frequently encounter crashes. In fuzzing the first 2 drivers, A and B, we encountered crashes caused by known bugs that have already been found by Syzkaller, and the throughput of snapshot approaches are much higher in fuzzing these 2 drivers. Interestingly, we found an unknown bug in the latter, which has not been found by Syzkaller. Syzkaller was repeatedly crashing on a known bug, barely making progress further than that. Next, by comparing our dynamic checkpointing with a single snapshot approach, we can see how effective our checkpoints were as created and managed by our dynamic checkpointing policies. By leveraging multiple checkpoints created deeper in the execution, the throughput was consistently improved in all experiments. Finally, when we compare Agamotto with an unmodified Syzkaller, we can see that in all experiments, the fuzzing throughput was maintained consistently higher. As Agamotto fast forwards through not only the crashes, but also the repeatedly executed parts of test cases, despite the added overhead of checkpointing and checkpoint restoration. For more results, please take a look at the paper. I'd like to conclude the talk with the following 3 key takeaways. State-of-the-art fuzzing algorithms already produce similar test cases in a short time frame, which we found to be another dimension to accelerate fuzzing. Leveraging that dimension, we showed that lightweight virtual machine checkpointing with dynamic checkpoint management policies can automatically accelerate kernel driver fuzzing. And last, which is more of a future work, changes to the fuzzing algorithms can be explored. More specifically, the sequence of the test cases generated by a specific fuzzing algorithm could be optimized together with the checkpoint creation and eviction policies. Thank you for your attention and listening.